Hey guys, thank you for watching this lecture. So, in this lecture, I want to talk about state, system, and process. Okay, so as I mentioned before, I'm gonna just go over some examples as I told you before. So, and in the beginning, I will tell you the specific pages on the lecture notes, on the PowerPoints that are uploaded on the website, on the Blackboard. So it might be helpful if I tell you the page in advance, so then you can pause, you can go there, take a look at there, read all the sentences, and then come back and continue watching this lecture. And I'll go over those concepts, but I mean, like, meanwhile, as I am solving an example. Okay, so now let's talk about a system. So here I'm going to talk about how do we define a system. Okay, as an example, let's say you're in a gas station and you're taking gas. So here's your car, an old one, the wheels and stuff, and then you're taking gas, right? So let's say here's your tank. It is a tank, the gas tank. And then here's the nozzle. So there's a gas flow. And simple, right? And then let's say the question is about the gas. It might be about the flow rate, it might be about temperature, volume, all these properties that we have faced so far, right? But it will be particular, let's imagine, it is particularly about the gas. Okay? So, in this case, the first step that we need to take is to define our system, right? But before defining the system and pick and then go over the solution and equations, we need to ask ourselves a question. It's a critical question. What are we interested in? And also, our point of view. What do I mean by that? In this case, we have two options. We can pick just the tank, the body, and then define inlet, which is the nozzle, or outlet if there's any leaking, and then we can continue solving the question. In the other case, we can just zoom and concentrate on the gas, and as we're taking the gas, the system, which is just the gas, is going to expand, right? Because there's going to be more gas in the tank. So it depends on your point of view. You're just going to pick the tank as a fixed volume and imagine there's a little opening that the gas is coming in, or you just want to zoom in and just concentrate on the gas and imagine it's expanding. So think about it a little bit more and imagine which one of these two points of view you want to take. So let me go into detail about this. So we have two options. One option is an open system. So when I mean by open, what do I mean by open? It's about mass. So when I say open, I am talking about mass, which means mass is allowed to be transferred. Or a closed system. Again, closed, I mean mass. Okay. So, let me tell you again. only focus on the gas as it is expanding, or concentrate on the tank body? Which one is open? The tank. Because I mentioned that we should imagine a little opening for the tank, that the nozzle goes in and then it infuses the fuel inside our system, right? So when you are talking, when you pick an open system, it means that you are interested in a fixed volume, which is the tank body. But when you talk about a closed system, you are only interested in a fixed mass, which is the fuel, is the gas. In this case, volume is constant. Here, volume changes. The system here is the tank. Here is the tank. Here the system is the gas. It's a little bit tricky because here in the tank, in the left system, tank includes the gas, right? But I'm repeating this again. It's just a point of view. How do we look at the system? Let me give you another example. Again, open system and a closed system. Before I switch to the other topic, let me address here that you might want to take a look at lecture number 1, pages 1, 2, 3. Okay, here for the open system, check lecture number 1, page 5. And for a closed system, again, number 1, page 4. A typical example for an open system can be a turbine or a compressor. These are two common examples. And here, piston cylinder. Okay? So, in an open system, we're going to talk about a fixed volume. So we just concentrate, we focus on a fixed volume. And mass can come in and go out. Energy can come in and go out. So if I pick a turbine, mass and energy are coming in and leaving the system, right? And also only energy is allowed to leave the system through the boundaries of the body of this turbine. Only energy. because let's say it's perfectly sealed. On the other side, I have a piston cylinder device, right? The piston is relaxed on this gas underneath, and it can freely move, and the body and the walls are perfectly sealed, so only energy can leave the system, not the mass. Again, this is a closed system, no mass. Unless there's an opening there somewhere, an exit or inlet or leaking or something. So in this case, in an open system, we are working with imaginary boundary. And in a piston cylinder, you're only talking about a specific amount of mass underneath the piston, which is trapped here, right? So, and the boundaries are real, the walls and the piston. So, real boundary. Okay. In this case, in the left case here, the boundaries are called control surface, right? But here they're just walls, right? They're real. So that's it for like a comparison between a closed system and open system, how to repeat a system before we go into detail, and I will go into detail later on in other examples. The second topic that I want to talk about here is state. Okay, state and process. So, take a look at the presentation, the lecture number 1, page 6. When we talk about an state, when we talk about a state in a particular example, we focus on some specific properties. Imagine I am plotting pressure versus volume. Okay, when I talk about state 1, I am talking about a specific point on this plot, for example here, and then the corresponding pressure and volume are going to be P1 and V1, right? And then meanwhile, as I warm up the system, do work or gain work or do chemical reaction or all these some sort of energy transfer, which is like heat or work, can be either in heat or work type. When I go through all of these transfers, I am going through a process, and process is a path in between two states. So from state 1 we go to state 2. So the properties, intensive properties, are changing. Pressure, volume, let's say a specific volume because I'm mentioning intensive, it should be per mass. And temperature are changing from the state 1 to state 2. Let's say here. Again, the corresponding properties are going to be P2 and V2. And this path from point 1 here, point 1 to point 2 can be in any shape. It might be linear, or it might be like curved facing downward or upward, or it depends on how we are changing pressure and volume. Let's say it's like that, right? So please note, on your graphs you need to clearly show the direction of the process, either by arrow or numbers, like 1, 2, 2, 2, 2, 3, 4, whatever. So keep this in mind. If I divide these two concepts, state and process, the two categories, for state we define a particular like property, like pressure, like P1, V1, T1, V2. See, all these notations show that we are talking about a specific property, like the pressure. We know the pressure at that time is something, right? Or you talk about energy, right? We say that our system has 2,000 kilojoules, right? So this is the state. When we talk about energy, just energy specifically, we talk about a state. Or there's another point that I should address here, is that at some specific states we are able to define equilibrium. Okay. So equilibrium can be established at a particular state. Okay. But on the other side, on the process, we're going to talk about a change, delta P or delta V or delta T, right? Or by, like in another case, we say P1-2 from state 1 to state 2, right? Or like V2-4, for example. And in this case, we do not talk about energy. Instead, we talk about heat or work. So, if a question mentions anything about heat or work, you cannot think about equilibrium. You cannot think about state, because it's telling you that a process is going on. When we say heat, it means a constant energy is coming into our system. Or if it says that the system is doing work, then it means that a constant flow of energy is leaving the system. It's a process. Until we stop, everything gets to the steady, everything gets to the equilibrium, and then we know now the pressure is P, for example, 8, and it's gonna stay on that value forever, right? Because it's equilibrium, until we don't have any fluctuation. So when we talk about a process, equilibrium cannot be established. Keep in mind, cannot be established, because as long as the process is going on, no equilibrium, nothing. So well, let me mention here that these 2 and 4, these are states. Okay, and then another again, I forgot to tell you that please take a look at pages 9 and 10. Thanks. And for this topic, which is called steady, this is the last one, steady flow process, check pages, lecture number 1, pages 11 and 12. Awesome. Now, when we talk about steady flow process, again, keep in mind that we are not talking about a state. We are not talking about a particular condition of the system. Everything is changing. It's a process. Something is going on, right? But when we talk about steady flow, now we are focused. We are talking about time. So far, I did not mention anything about time. Well, it's tricky. When you talk about a process, when I was talking about here about a process needs time to happen, right? But then this process might be in a special case, which is a steady state. So a process, let's say, let me define it this way. So a process can be defined in 2 ways: steady in time and transient in time again. What does that mean? It means that if I measure, let's say I have a turbine, okay? If I measure pressure, volume, and temperature at the inlet and outlet of my turbine today, I go home, I come back tomorrow. If I measure pressure, volume, and temperature, these intensive properties, on inlet and outlet, again, I will measure same thing. This is steady in time, right? But if the pressure, even one of these properties, if it changed the day after, then the whole process that was going on last night, the night before, overnight, was not steady because one of the properties changed. And so now we talk about 2 different times, right? So when you say that something is steady, the process is steady, it means that, as I mentioned before, let me write it another way. Pressure, volume, and temperature at T1 equals to pressure, volume, and temperature at T2. These are time. So just keep in mind that we might talk about state, and if we go through one state to the other one through a path, it's going to be a process, and this process might be steady in time or transient. I will show you, I will recall all these concepts that I talked about in this lecture in future, and meanwhile I'm solving one example. Thank you for watching this.